So the solutions I've already done, at least the ones posted, 1 through like 6 or 7. And so hopefully you can read through those. I'm thinking I'll do 1 or 2 of them at the beginning and then maybe jump down to the bottom. Let's see. Walk you through maybe number 7 and 8 because then that might be more useful. Okay. So at the beginning here, you should already know what must be true for the mean value theorem to apply. And that is, we have to be given a situation with a function that's continuous on some particular closed interval and differentiable on that same open interval. I think it's probably best to start off with a picture. You know, e to the x is continuous on any interval, including this one. So we'll start off with y equals e to the x is continuous on the closed interval -1 to 3 and is differentiable on that same open interval -1 to 3. Now we could say e to the x is continuous and differentiable everywhere, but because that's not the case for all functions, I think it's best to practice that, hey, continuous on the closed interval, differentiable on the open interval in case it comes up. Okay, so we need to finish off, so the mean value theorem applies. And as you know, I'm not a fan of abbreviations. Okay, so what does the mean value theorem say? It says that the slope, and I don't have really good notation here. I can't say like f prime of c or something like that. So on the left-hand side, instead of f prime of c, slope of this function at a point, just so it's very obvious, I'm doing the derivative of e to the x at x equals c. And let's see, what's that going to be equal to? That's going to be equal to, you know, we'd like to write f of 3, but we weren't given a function named f, so we're going to say e cubed minus e to the -1 over 3 minus -1. And so we can replace the left-hand side with e to the c, and what is this? E cubed minus 1 over e over 4. And you know, clearly this is a calculator sort of thing, so we need to take natural log of both sides to get to that c. And c is equal to the natural log of e cubed minus 1 over e over 4. And I suppose we could grab a calculator for that. I probably should have had that ready, but whatever. So, well, that's going to take me too long on a calculator. Who cares? Okay, so that's the basic stuff. Let's go to something a little bit more difficult down here on number 7. And number 7, I think it's pretty easy. The first thing I notice is that x minus 1 and x squared over x minus 1 is discontinuous. We don't have to prove this. At x equals 1, and that's a problem because 1 is definitely on our closed interval -3 to 3, so we can say, so the mean value theorem does not apply. All right. I love it when that happens. Dang, what about this graph? So the cube root of x squared minus 9. Well, let's see. X squared minus 9. Oh, doesn't even have to be positive, does it? Because it's a cube root. Well, you know what? I'm going to go ahead and cheat here, and I'll show you what I mean. X squared minus 9 to the 1/3 power. So that derivative is 1/3 of x squared minus 9 to the negative 2/3 chain rule times 2x. So y prime is 2x over 3 times the cube root of x squared minus 9. And so this graph, let's see. This graph is undefined where 3 times the cube root of x squared minus 9 is equal to 0, and that's at x equals 3, x equals negative 3. And so because 3 is on our interval, we can say the mean value theorem does not apply. So on the last time we said that, we said something like our graph was discontinuous. Now here our graph is going to be continuous everywhere, even though we don't know that graph. You can check it out, graph it on Desmos or your calculator. What do we know? Y equals the cube root of x squared minus 9 is not differentiable at x equals 3. So we want to choose that one, not the negative 3, because remember the mean value theorem says a function has to be continuous on the closed interval, so in this case the entire negative 3 to 6, and differentiable on the open interval negative 3 to 6. And so, you know, this negative 3 down here, that doesn't really cause us any problems because that's at the end point of an interval we're not using. All right, let's do one more. Ooh, a semicircle. I know pretty early some people are going to think, oh, I don't have to do anything because no closed interval is given, but no closed interval is given explicitly. If you know this is a semicircle, centered at 0, 0, and you can kind of tell. Let's see, if I put in x equals 0, we get 0, 4. If we put in x equals 4, we get 0. X equals negative 4, spits out 0. And I'm sure there's some stuff in the middle there too. But I guess what I'm thinking, if I squared both sides and made sure we only kept the positives, then we could rearrange to have x squared plus y squared equals 16. But again, we're just keeping the top half here. Why are we only keeping the top half? Because we weren't given the plus minus here, we were given the function version. Okay, so let's see. Y equals the square root of 16 minus x squared is indeed continuous on the closed interval negative 4 to 4 and is differentiable on the open interval negative 4 to 4. So here's one of those cases, if you didn't realize, just kind of memorizing stuff might help, because this graph is not differentiable at the endpoints x equals 4 and x equals negative 4. This graph has vertical tangents there. So, I don't know, some people that are a little imprecise would say, hey, the mean value theorem doesn't apply. Anyways, it does. So the mean value theorem applies. And let's see if we can go ahead and set this up. So on the right-hand side, that's going to be pretty easy. By the way, this is a Rolle's theorem case. Because the y values of the endpoints are equal. I'm not going to write that out because I don't want to do the extra writing. But just realize when you're asked about Rolle's theorem, that's mean value theorem plus the y values of the endpoints match, which means we're going to get a horizontal tangent somewhere in between the endpoints. Anyways, so we need derivative on one side equals average rate of change on the other. So I think I'm going to write 16 minus 4 squared or I'm sorry, the square root, minus the square root of 16 minus negative 4 squared, all over 4 minus negative 4. And what goes on the left? Why is this flashing? I don't know. What goes on the left? The derivative of 16 minus x squared, except we're going to throw in a c. So that would be 1 over 2 times the square root of 16 minus x squared, I'll write c squared, chain rule times negative 2c. Okay. So let's see, that's going to be c over negative square root of 16 minus c squared. That algebra is going to be interesting, but I guess it helps to know we're looking for this whole thing. Oh yeah, the right-hand side is equal to 0. So it doesn't really matter what we do with the algebra. You know, multiplying to get rid of that denominator, we get c equals 0. Dang, that turned out pretty well.